And on the next slide, we did a study, it's a whole night, and the graph here shows the basic shape of the turbine place. Again, starting the high per sound, we'll see sound. By the time we get to the speed break, we are at much lower levels. And what we find is that over that night, when wind speeds were less than 10 miles an hour, we still 10 miles per hour, we still had sound level at the receiving property of 51 to 52 dBA, 10% of the time. And again, you have to remember that we're talking about that pushing sound that we heard earlier. Just one of the things that wind turbine companies, I don't want to say this, like to do is to say that their initial estimates when the impact on the computer have been tested, and they find high degree of correlation between predictions and the result. They find a high degree of correlation between the predicted sound levels from their computer models and what they find after the wind turbines are operating. In the state of Maine, this is a study at Hunts Hill. The Maine Environmental Protection Agency funded a full season study of the sound levels based at Hunts Hill. Now, all of these homes are about 2,500 feet from the nearest turbine, and in some cases about 1,000 feet. What they found over the course of that year is that the sound could range anywhere from a moderate 35 decibels all the way up into the low 50 dBA range. And under all of these conditions, these data samples that you see on the chart picked as times when the wind turbines cleared the noise source. All of these dots represent a time when the wind turbine was clearly the dominant noise source. So what we see is that little changes in weather, little changes in the way the turbines are operated can make a difference of the sound in a property of 35 to 50 decibels, of almost 20 decibel change. So when a person says they have a computer model showing that a wind project will be compatible with community, there is a presumption that the numbers are accurate. But what we find in the real world is that they could range anywhere from 5 decibels to 10 decibels above or below those predictions. Next slide. The other thing I'd like to point out, that when you have wind turbines located on a ridge, they typically end up being arranged in one row. When wind turbines are located on ridges, they end up being a long row of turbines. They follow the ridge top line. When noise sources are lined up in rows, the sound that propagates off of them changes dramatically. It propagates at a different rate than it does if we had wind turbines randomly scattered on the planet, for example. This is kind of a technical acoustical engineering detail, but what we've been finding is that wind developers are using the point source model, which assumes that for every time you dump, the distance between the noise source and the receiver at sound level drop of 6 decibels. When turbines are broken, that is not true. It drops off at 3 decibels. That's that this is one of the reasons why when you have bridge-mounted wind turbines, the setback distance needs to be almost double what it is for randomly distributed turbines for flat turbine. And I'll just, I guess, summarize it. Normally, we recommend that wind turbines be 1.25 miles from the nearest home. But when we have a bridge-mounted wind turbine where they line up in rows, that distance needs to be 2 miles to 2.5 miles. You know, when we have wind turbines in a row, as they are typically located on bridges, the setback distance needs to be doubled, or it needs to be 2 miles to 2.5 miles, in order to get the same protection as we would get at quarter miles if the wind turbines were on the line in a random distribution.
Are you talking into the microphone, or are you moving your head? Sounds like you're moving your head when you're talking. Oh, it's cool.
Ask them to speak a little louder and project your voice right into the microphone. Or just as well.
Okay, yep. I'm gonna try and turn it up just a bit.
Maybe see if you can do anything to. It's a little bit like being tortured by a wind turbine, I think.
Is it?
Yeah, it's sort of coming in and out, in and out. So
that's amplitude modulation.
yes, well, we are all experiencing it.
If we could have a large truck pulling into the back so you get the rumble, then we'd have the full effect. Let's go to slide 21. Okay, what I'm showing on this slide is a typical, this is a contour map from a wind developer where the wind turbines are laid out in rows. The developer used a point source model in order to show that the homes, which are in green areas, would be protected. By using, if they had used a line source model, then as the red arrows show, the yellow areas would have doubled up to where the green areas are now. And the green areas would extend out to where the blue areas are. That would have made the project exceed the state limits. So, since you have ridge-mounted wind turbines, you need to be sure that the developer makes his estimates using line source. Next slide. One of my first projects was in Wisconsin, called Blue Sky. In this area, the farmers have the wind turbines randomly located throughout the farmland. And when the project was first started, the vast majority of people in the community were in favor of it. Now that the project has run for about a year, a survey of the people has found interesting changes in attitudes. First, 60% of residents say that if they have to do it over again, they would not want wind turbines on their property or near their home. At 60% regret the decision they made to go. 57% believe they lost property. 4% believe that it's increased. 56% say they have problems with TV and vapor reception. 52% experience shadow flow. 49% have problems with 30% have problems with self-perception. 22% have no problems.